Hello, welcome back to my Calculus 1 playlist. In today's video, we're going to continue our discussion with functions, and more specifically, we're going to define even, odd, or neither functions and go over some examples. So without further ado, let's start. So let's define what an even function actually is. So even. So a formal definition, an even function is a function that can be represented by the following. F of negative x is equal to f of x. So if this statement is true, if f of negative x is equal to f of x right here, we have an even function. That's it. So let's look at an example of that. Say we have f of x is equal to x squared. For a function to be even, we need to have f of negative x is equal to f of x. So let's check this. So we do f of negative x, and to compute this, we just plug in negative x in every place where x is. So we have negative x, and we square this value. That turns out to be x squared, just from the rule of squaring, and that is equal to f of x. So because f of negative x equals to f of x, and that is true, we can say the function is even. Pretty straightforward. Let's look at another example. Say we have g of x equal to x squared plus 2x to the 4. Great. So now for this to be an even function, g of x to be an even function, we need g of negative x to equal to g of x. So again, plugging in negative x to every place where there is an x, we have negative x squared plus 2 negative x to the 4. Great. We can simplify this to be x squared plus 2x to the 4, which is simply just equal to g of x. Again, since g of negative x is equal to g of x is true, we can say that the function is even. Very straightforward. Let's talk about one of the properties about even functions. Okay. I'm going to draw f of x is equal to x squared, because we've seen that that's already an even function. This is the graph of f of x is equal to x squared. So great. So a property of all even functions is that they're symmetrical about the y-axis. So if you reflect an even function across the y-axis, you will get the exact same sort of mapping. You'll get the reflected version of the function, which is a really interesting property. And you'll find that this is a useful property whilst we do integration in the very future, not near future, but in the future of this course. It'll be something that's addressed in this course. So you don't have to keep note of it right now, but this is just a really interesting property to remember about even functions. Even functions are symmetrical about the y-axis. Great. Now let's talk about odd functions. So a function is defined as odd if the following is true. So if we have f of negative x, it needs to equal to negative f of x. Odd function. So very similar to the even function. The even function, where f of negative x is equal to f of x, is the definition of an even function. The odd function is defined as f of negative x is equal to negative f of x. So let's look at some examples of odd functions. F of x is equal to x cubed. So if we plug in f of negative x, we see that we obtain negative x cubed, which is just equal to negative x cubed. In this case, f of negative x is equal to negative f of x right here. See, we have f of x right here, and we have negative in front. Therefore, we can say this function is odd. Moving forward, if we look at this example, f of x is equal to x, we can then do f of negative x is equal to negative x. This is equal to negative f of x. Since f of negative x is equal to negative f of x, we can say that the function is odd. Pretty straightforward. Let's look at the case that we have neither odd nor even function. And you could guess it. This just means f of negative x is equal to f of x. So this coming from even. Or f of negative x equals to negative f of x. This coming from the odd function rule is not true for a function. Perfect. So let's look at an example to see if a function is odd, even, or neither. So example. Be our last example today. We looked at 2 where we know it was even and 2 where we know it's odd, and we'll go through one example where we check if a function is even, odd, or neither. And actually before that, I didn't define a nice rule for odd functions regarding their geometry. So let's talk about that. Oops. So let's say we have f of x is equal to x cubed. Then we have this function. We say that it is symmetric about the origin. This is x, this is y, and this is f of x. Meaning, one way I like to look at it is if you reflect this positive portion across the y-axis, and then you reflect again about the x-axis, it gives you your reflected version. So an odd function is symmetric about the origin. And again, this will come up in the future of this course during integration and other parts. So you can kind of try and remember that. But anyways, let's look at this in an example. So say f of x is equal to negative 2 over x plus x squared plus 3x cubed. Let's see if this is even, odd, or neither. So let's check case by case, even first. So to check the even case, we do the following. F of negative x is equal to f of x. We need to check if that's true. So we plug in negative x to everywhere we see an x. So that gives us negative 2 negative x plus negative x squared plus 3 negative x cubed. This is equal to 2 over x plus x squared minus 3x cubed. Is this the same as our original function? Well, it turns out no. We don't have a negative sign in front of this term. This term is positive, so that's good, but this term is negative. So we know that this is not even. It would need to be the exact same as the original function. In the odd case, so we've already computed what f of negative x is equal to, but in the odd case, we need f of negative x to equal to negative f of x. So let's pull out a negative sign and see what we get. So for f of negative x, we would pull out a negative and go 2 over x, and there's a negative sign in front of that, minus x squared, and then you'd have a positive 3x cubed. And now let's compare that to the original function. These two terms are the same, but these two terms are not the same, whilst these two terms are the same. Because not all the terms are the same, when we pull out this negative sign, we can say that we do not have an odd function. Not odd. Therefore, f of x is neither even nor odd. And there you have it. Pretty straightforward stuff. It's a pretty easy problem to work through, defining a function, whether it's even or odd. So we said that even functions must have the property f of negative x is equal to f of x, and that they are symmetric about the y-axis. That's really important to understand, as well as odd functions have the property f of negative x is equal to negative f of x, and they are symmetric about the origin. And we learned how to go through systematically how to check if a function is even, odd, or neither. So you just check the even case, you check the odd case using f of negative x, and if it's neither, it's neither. So I hope you all enjoyed, and I will see you in the next video. Take care.